not it started. Yeah, started. Good. Right. So today's class, it is August 3. So today also we'll be getting into the, so as a recap, right? Standards at high frequencies. Right, were mentioned in terms of power and impedance, were mentioned in terms of power and impedance, not in terms of V and I. Shilpa, you're there?
Yes, sir.
Shilpa, this was the statement that we discussed in class yesterday. Can you just give me the significance of the statement?
That it's better to use power and impedance instead of voltage and current.
Yeah, I didn't ask you to read the statement, Shilpa. I just wanted you to tell what is it.
That is what it says.
Right, Shilpa, thank you. Shravya, come into picture. Shravya.
Yes, sir.
Shravya, what was it that we were discussing in yesterday's class? Can you come up with it? I have written it in as a statement. Are you able to see the Word document? Are you able to see the statement?
Yes, sir. Yes, sir.
Yeah.
I can see.
Yeah, see. So please explain that statement.
Sorry, sir. I can't remember.
You can't remember. Saurabh. Okay. Praneeth. Not there. Right. Akshay. 2 to 4. Akshay.
Sir.
Akshay, please explain the statement. What were we discussing in the last class?
I could not recall.
Yeah. Okay.
Frequencies in terms of power, I think.
Frequencies in terms of power. So how will you express 1 gigahertz in terms of watts? Tell me.
No
idea. Right. So Narendran. Right.
Hello, sir.
Yeah, Narendran, tell me what were we
Sir,
discussing?
I'm Praneeth actually.
Praneeth, okay, Praneeth, tell me.
Sir, we are thinking of a device wherein it calculates VI and accordingly calculates the power, which is standardized. And that is what results in power calculation.
Okay, right. Right. So guys, again and again, thank you, Praneeth. So everybody get into listening mode. So again and again, I'm emphasizing the fact that at high frequencies, why we are taking all these struggle, right? You have understood what is called as a front end. Front end is mainly involved. The hardware of the front end is very critical because it communicates with the external environment. So they went for standardization. And while doing the standardization, the effect of electrical length became predominant. Because of the electrical lengths, clear? Here I have to put a small semicolon. The frequencies involved were from 900 megahertz to 6 gigahertz. In these frequencies, if you look at the wavelength and if you look at the devices that we make, they were all in the same range. That was what I was trying to tell yesterday. At 1 gigahertz, the wavelength is 10 centimeter. So at 2 gigahertz, it is 15 centimeter. So if you look, your cell phone is operating in 969 megahertz. Clear? So the wavelengths and the device length are comparable in this range. So what happens? You will have immense phase shifts inside the device. This was what the concept of electrical length. So all your devices are now electrically long. In that, there will be phase changes within the device. Clear? When there are phase changes, you can't measure voltages and current so easily. So what happened? They decided that they will always talk in terms of V into I or V by I. Clear? That is why I gave the examples of RS-232 and RS-484 TTL logic, where everything was expressed in terms of voltages. Everything was expressed in terms of currents. Clear? Right? But in a microwave device, it will not be given like that. It will be given in terms of power and impedances. This is the idea. Right? So, Yadishwaran.
Yes, sir. Yes, sir.
Yadishwaran, unga cell phone charger illati laptop charger la have you seen the current and voltage specifications?
Yes, sir.
Yeah. Can you tell me one specification?
Around 3 amps and 12 volts or
3 amps. God.
yes, sir.
Is
I
it
seen
0.3 or 3?
Sir,
Look at, is it 0.3 or 3?
I seen both, sir.
Yeah. So for your mobile phone, do you know what is it?
For mine, it's 3 amps and 5 volts, I think, sir.
3 amps and 5 volts. So you need 15 into 3, 45 watts for your mobile phone to get charged?
15 volts, sir. 5 into 3.
5 into 3. Okay. So everybody just look at it. Samira.
Yes, sir.
Samira,
Yes.
what is the specification of your laptop charger or anything, or mobile phone charger, or whatever is nearby you? Anything.
Sir, it's 1.5 amps. Hello?
Yeah, I'm there.
Sir, I think it's 1.5 or 2.25 amps, sir.
Okay, great. Good. Srija.
Yes, sir. Yes, sir.
Srija, all these people told some voltages and currents, correct?
Yes, sir.
Right. Now, cell phone, isn't it a microwave device? Why were we telling in terms of voltages and currents?
Yes, sir. Oh, 1 second.
Then what was the meaning of whatever I was taking in the class?
Oh. The meaning, like how I didn't get the question, sir.
Thank you, Srija. I'll put it to somebody else. Sharanya. Right. Okay, Venkatesh. Okay, right. Jai Hari.
Yes, sir.
Jai Hari, you were involved in the you heard whatever was happening in the last 5 minutes. I asked many people about the specification of the charges. Did you hear that?
Yes, sir.
Yeah, they all told us in terms of voltages and currents, no? Correct?
Yes, sir.
But isn't a mobile phone a microwave device? They should have told it in terms of power, no? Why did they tell it in terms of voltages and currents? Then whatever I was taking in the class is gone for a sick toss, isn't it?
Yes, sir. Sir, I'm not entirely sure what the answer is.
It's okay. Right. Anybody can come up with the answer. I have put out a very useless question actually. Can anybody bring out the answer? Why the question that I asked itself was useless?
Sir, how is microwave?
One of you. Who was it?
how is mobile charging microwave, sir?
That's it. Thank you. The mobile charging is done using 50 hertz electricity supply connection that is coming from your plug point, right? So there it is at a low frequency level where your devices are expressed in terms of voltages and currents. Thank you. Clear. So get to know these facts, right? And we have never been exposed to high frequency electronics. This is another thing that I am trying to tell. Whatever high frequency electronics you are exposed to is coming in a packaged form, right? Shriram.
Yes, sir.
Have you heard of the term specific absorption rate of your mobile phone?
Yes, I have heard it somewhere.
Yeah. Can anybody tell me what is the specific absorption rate of your mobile phone which you are having? Anybody? Okay, if that is not the case, I request everybody to go and see the specific absorption rate of your mobile phone that will be expressed in terms of watts. Get the feel there, because there it is directly dealing with the cell phone. Specific absorption rate is the amount of radiation, almost the amount of radiation, that unwanted radiation that your mobile phone gives. So that is a microwave quantity. The field is at the microwave level, so they started expressing it in terms of watts per kilogram. Clear? So trying to give you an idea of all these ideas. So now let us just try to, I'm just see, still now I am keeping on telling that I am going to introduce S matrix, but I personally feel that you have to get to know the entire story before you get into S matrix. Only then you will understand why it is commercially so easy to use. Right. So when the device is operating at high frequency, there is no meaning in telling in terms of V and I. We need to tell in terms of V into I or V by I. Right. So what happened is predominantly this arises because of when we had waveguides. What was developed for waveguides then later came into thing for everywhere. Waveguides, right? So I'm just telling you again a bit of history aspect here. See, waveguide was a simple metallic tube, right? Where it got an output and where you gave an input, right? Both were in waveform. Wave means I'm telling it in terms of field. So it was impossible to measure the voltages and currents, right? So what happened? They wanted quick analysis. They wanted quick analysis, right? Like how we do in circuits, right? So what they did is, what they did. Right, the first point is they devised something called as a vector network analyzer. This is a standard device. You can call it even as a high frequency voltmeter. Right, this was standardized. A high frequency voltmeter by the name vector network analyzer was standardized. Clear? Detectors, right, that could convert field to a voltage was standardized. Along with the VNA. Right. So these detectors always gave out a equivalent. Sorry. So they devised these things, detectors that could convert field to voltage. So detector got field as input and gave an equivalent voltage. Gave an equivalent voltage as output. Right? Now what happened is you have the regular waveguide piece. Right? This is the regular waveguide with input and output. You had detectors. Detector, I'll just give it like this, detectors. Right? Which will give field and it will give a voltage. Right? This was connected at the output, right? And you had a VNA. Right? Now detector output is connected to the VNA. That's all. So you had the arrangement like this. The device under test, which I'll call it as DUT. Then you had the detector. Then you had the VNA. Right? So this, the VNA gave an output. Right? This was what was called as an S matrix. It gave out a matrix representation. Right? They actually tailored the VNA to give out a matrix representation because, right? Why they wanted a matrix representation is at that time, circuit analysis was really popular. Circuit analysis was highly popular. Right? Things like Z matrix, right? Impedance matrix, admittance matrix. You would have studied something called as H matrix. Varsha, have you heard of something called as H matrix of a transistor? Varsha?
No, sir.
Electronic circuits la 4th semester la you didn't learn of HFE. HFE nu padichirupingle.
Yes, sir.
Similar-
We did H matrix.
H matrix, hybrid matrix of a transistor.
Yes, sir. Yeah.
Yeah, who was it actually?
Sriram.
Sriram, what did the H matrix try to do?
So there are two inputs and two outputs. So it's not a single input, single output. So it basically is a matrix which gives the relation between each input terminal to the output terminal. So
Yeah.
the output in terms of each of the input and input in terms of each of the output.
Good.
Matrix.
Right. So this matrix representation, what is the beauty of it? Matrix representation of devices or circuits. Right? This gives relation between the ports, right? Directly it just gives the relation between ports. So this was considered as a beautiful way for quick analysis, relation between ports, right? No need to you just need to measure quantities, measure the quantities at the ports and express them as ratios. Express them as ratios. Right. This gave a tool for quick analysis. So we actually knew if it was an amplifier, what should have been the relation. If it was a filter, what should have been the relation. This gave a tool for quick or rapid analysis. Quick or rapid analysis. Right. So this was what the idea of matrix representation itself. So our S matrix is trying to provide it at high frequencies. So at high frequencies, to measure the voltages and currents, we designed the VNA and the detectors suitably, and hence now the entire story is now complete. What is meant by a S matrix or a scattering matrix? Clear. So now if you are completely comfortable with this idea, I'll be really happy. Why we went for matrix representation? Clear. And what is matrix representation? Just measure the quantities at the ports and express them as ratios. That's all. Don't worry about what is inside and out. Clear. Because for a transistor, if you take only thing, that HFE became a gain parameter because it was always measuring the output voltage and the input voltage. So you called it as a gain. You had the input impedance also, HIE, input impedance, where you measure the input current and the input voltage. So finally, there is a small thing. What is meant by a port? Port is any point where you can measure a quantity, where you can measure VIP. VIP means voltage, current and power. Please understand that correctly. It's really difficult to write entire things here. Right. So this was the idea of the matrix representation. Now it should be very clear. So wherever you go for high frequency measurements, there will be a VNA associated with the set of detectors. You just need to place your device there, connect it, and that's all. You will get an S matrix representation. So the final thing will be you will have a VNA, right? This is your device under test. This is port 1. This is port 2. All you need to do is you have detectors. Connect it here, connect it here. You have detectors. Connect it here, connect it here. This will provide you an S matrix. That's all. Right. So hope you are able to understand the idea here. This S matrix is what we are now going to theoretically study. Clear? At a hardware level, the vector network analyzer gives you the S matrix. Now we are going to see what is the explanation behind each of those values and how it can be understood. Clear? Similar, just as how you saw that HFE was equivalent to gain, HIE was equivalent to input impedance. Just as you decided these things, the S matrix, the individual elements of the S matrix should be understood. So for that, we need to know what is the definition of each of the idea of S matrix. So what does S matrix, the S stands for? S stands for scattering matrix. Right, and it is also called as a scattering parameter. Right, why it is called scattering and all? Because back to the waveguide, in waveguide you were measuring fields and you are getting a something called as a scattered voltage. From that aspect, it was named as a scattering parameter. You were not measuring the actual voltages. You were only measuring an approximately equivalent voltage. So this gave an idea of this scattering parameters, and the collection of scattering parameters is called scattering matrix. Is the idea clear? Has anybody got any doubts regarding this thing? Because next I am just going to directly get into the idea of definition of S matrix. Till now it was just what. Has anybody got any problem clarification here? Right, what started with waveguide, we thought that we will use it for everything in the range 900 megahertz to 6 gigahertz, where measurements of voltages and currents individually was difficult. Right, is the idea clear? So if that is the case, let us just get into it. So the definitions can be told only from perspective of a waveguide device, where wave is given as input and wave is taken as output. right? And you will be doing power measurements. Clear? So that is the experimental part of it. Let us see the analytical explanation for S matrix. Analytical explanation for S matrix.
Sir, I've got a doubt.
Yeah, please.
Sir, this S matrix is mainly used for microwaves, right? For higher frequencies.
Yeah, definitely. Yeah.
So then, is it like applicable to all the higher frequencies, like from 900 megahertz to 6 gigahertz? The S matrix will remain same.
Need not be. If it is a filter, the S matrix will change, no? Depending on the device under test, the S matrix will change.
Oh.
Getting it? Do you understand? See, any electronic component, but if you are in this frequency range, you characterize it by S matrix. Getting it? That is the main aim of, correct?
Yes, sir.
Getting it? See, for example, you are designing a filter in this range. Who is that? Akash? Is it?
Yes, sir.
Akash, you are designing a filter which has to work in the band 2 gigahertz to 3 gigahertz. It should be nil outside these things. Is it okay? It's a band pass filter in 2 gigahertz to 3 gigahertz. Getting me?
Yes, sir. Yes, sir.
Filter is a 2-port network. You give one input, you take one output. Correct?
Yes, sir.
So in 2 gigahertz to 3 gigahertz, my relation between port 2 and port 1 should be 1. Correct? I'm just putting it directly, no? Output at port 2 should be equal to our input at port 1. If I take the ratio, it should be 1. Correct?
Correct.
Outside this band, it should be 0. If I take the relation 2 to 1.
Yes, outside it should be 0.
Correct. For a filter, this is the S matrix. Correct.
Understood, sir.
Right now, if it is an amplifier which is working in a very big range, you will expect 2 to 1 to be really a good positive number over an entire range. Getting it?
Yes, sir.
Right now, oscillator. How many ports does an oscillator have? The discussion is not only between me and Akash. Everybody can enter. Oscillator. How many ports are there?
There
Oscillator.
should be 2 ports, right? Means it one wave is.
Akash. Okay, Akash is given some rest. We'll have some discussions. Oscillator, how many ports? Can anybody come into picture? Praveen? 239. Praveen.
Yes, sir.
Oscillator, what is an oscillator doing? What is the functionality of an oscillator?
For a given frequency, it will generate a sinusoidal wave, sir.
It will generate a sinusoidal wave of given frequency. Okay. You won't give. What input do you give to an oscillator? Do you give any input to an oscillator?
Sir, I'm not sure, sir.
You are not sure. A big thing.
No, sir, no input.
What is who's that? Samita, input to an oscillator is 0. So how many ports are there for an oscillator?
I don't know, sir. I think no.
What is the definition of a port?
No, sir, it's a port, but that's a DC source.
This is the idea. Is the DC source power supply an input or not?
No, sir, that's not an input, that's a source.
Fantastic. That's good. So any electronic device, whether it is an amplifier also, you need a DC source, correct? I hope it's Varsha.
Yes, sir.
Varsha. Okay, Varsha, then oscillator has only one port. Can I tell it like that?
Yes, sir, the output port.
Just the output port. So there is, how will I write the relations? If there is only one port, how will I write the relations? Because I told you matrix representation itself means just measure the quantities at the individual ports and write relations, correct?
Yes, sir.
So for an oscillator, who will I be able to write whether it is at low frequency Z matrix or high frequency S matrix?
So will all the values look identical?
Will all the values look identical? Who was it?
So Thiruvikraman, sir.
Thiruvikraman. First of all, எவ்வளவு value இருக்கும் Thiruvikrama? That
Sir,
is
I'm not even sure, sir.
How
Sir,
many
it won't have
values?
an S matrix, sir.
Yarpa?
Sriram.
Tell me.
Sir, I don't think we have an S matrix because we don't have an input port. Since it's an oscillator, so the output will be in terms of time because it's oscillating with some frequency, right? So it will basically a function of time. I don't think we have an S matrix.
So let us just wait for it. Okay, so at present oscillator is a very interesting thing which can stop the discussion at any point of time. Anyway, what started with Akash, I think we went into little bit unknown domain. Akash, first of all, is your idea clear? What the doubt you had in your mind? Is that clear?
Yes, sir. Yes, sir.
Right. No confusions regarding the matrix representations and all. Clear?
Clear,
right?
sir.
Right. It is just the functionality you are expressing in this fashion.
Understood, sir.
Yes. Okay. Great. Okay. So let us just get into an analytical explanation for S matrix. Consider. I will just give out the analytical expression today, right? And I will stop today's class and I will request that everybody go through the text, read it once and then come prepared for the next class. Clear? Because it will be good if you do that. Consider a N-port device. Whenever we start an analytical thing, we take the most ideal thing. Consider an N-port device or a component or a collection of components right, which is called as a network in our terminology. Clear? If that is there, right, so this definition applies to anybody. So this is that device. This is either a device or a collection of components, anything I am putting it here, and there are N ports. Right, in circuit you would have accustomed yourselves to 2 ports, but the moment I gave oscillator, there are lots of confusion. So that all things we'll clarify. 1, 2, 3, 4, 5, 6, 7 and N ports. Okay, clear? So if this is a port device, right, and it is operating at high frequencies, right? Clear? It is connected to VNA. Right? So these are the things. Now the S parameter is given as Sij is given as Vi. Just a minute. Vi, I'll just give you some standard term. Vi minus by Vj plus Vk plus equal to 0. K not equal to I comma j. Please look at it carefully. Right? K not equal to I comma j. So what does this mean is V represents the equivalent voltage measured by VNA at any point, at any port. Right? So any V with a minus subscript is power going out from the port. from the port. Right, any V with the plus superscript is power coming into the port. Right, so now with this, if I put VISIJ means Vi minus the power going out from the ith port by the power coming into the jth port. Now what is the condition? Vk plus equal to 0. K not equal to, in the sense what I'm trying to tell is K should not be I and J. All the other ports, there should not be any input power. It is under this condition that S matrix is calibrated. So if you have something like this, I will tell this as V1 minus is the power going out. V1 plus is the power coming in. So you have a power coming in and a power going out. Right now, what is this power going out from the same port is? Right, when see, for example, if I give a power in first port, I can get a power output in second port. Clear, the second port may be connected to some other devices. The third port may be connected to some other devices. If there is an impedance mismatch among these two ports, there will be a reflection from this side. So these reflections are usually taken care by this input and output power. So what I am trying to tell is why we have this minus and plus representation. V minus and V plus requirement is to take care of reflections arising due to any impedance mismatch. Right, so as per a standard, there should not be any impedance mismatch, but if there is a mismatch, there will be reflections. To take care of these reflections alone, we are deciding on two specific descriptions, an outgoing power and an incoming power. Clear, so the Sij, the parameter shown by the vector network analyzer, is ratio of the two equivalent voltages measured at ports. Now, at a practical level, you don't need to know what is this equivalent voltage because the detector does that job. Only thing is, we will now what to do is, as I explained to Akash, if I have designed a filter, clear, it is a two-port network. I connect it to a VNA and I will check whether my S21 is correct in the particular frequency range. That's all. Clear. Now, if there is a two-port network, this is not an issue. If there is a three-port network, I will calibrate it like this. Clear. But during operation, if the third port is not satisfying this thing, what is this Vi minus by Vj plus Vk plus equal to 0 telling? When I am measuring between two ports, there should not be any input power in any ports. That's all. Right, that is what this is telling. When you are worried about two ports, when we are involved with two ports, power input at all ports should be 0. That's all. We are not worried about what is going out. There should not be any extra power that should come out. Right, now during actual operation, these are the issues. Right, we may find that, for example, a three-port network, the third port will be having some unwanted input. So just think like this, you have a three-port device. For example, in a field level application, you have a three-port device. Right, this is 1, this is 2, and this is 3. This is connected to some source or a circuit. This is connected to an antenna. This is connected to another device. right? Now S31 is measured with P in at 2 as 0. But commercially, when it is operating, suppose for example, you have used a transmission line in port 2 and there are reflections that may affect the device. Getting it? So practically during operation, during functioning, I'll write it like this, during functioning, P in at 2 may not be 0. Then S31 won't be the expected value. Because it was measured as P2 is 0, but commercially, but on operation level, it may not work. So this gave an idea that, so if you monitor S31, if you get the ratio of S31 and you find out it is not working out correctly, then they could find out that there must be some problem with 1 and 3 that we have to check out. But it also gave you a future idea that there may be some problem in port 2 also. This is what the beauty of S matrix. Clear? So you are connecting this device in in a radar system or in a communication system, and you are giving some input and output. Suddenly the required functionality is not coming out. So how to troubleshoot? Now you will take the S matrix of the device. You will see what is 3 and 1 correctly. Now when 2 is not given in, you can take this device, put it in a VNA, get the S matrix. But now when it is not working, it gives you an insight that there is some problem at 2. That is also one of the issues. The main idea being antennas wrong or source wrong, that also should be checked. But through this S matrix, we got a comprehensive idea that how to troubleshoot a device. This is the idea here. Right, I'm stopping today's class. Has everybody got an idea of what S matrix is? Why by just measuring power levels, we can troubleshoot a situation. That is the idea of matrix representation. So if I design a 3-port device, I will give it to a VNA and I will get the standard characterization. I will take the component, I will put it into field level operation. If it works perfectly, good. Otherwise, this matrix representation provides a scope for easy troubleshooting. This is the concept that everybody should understand. The idea of easy troubleshooting. This is what the matrix representation helps. So matrix representation helps in easy troubleshooting. That's all. This is the main thing that you should know. Right? We'll stop here. I'm expecting people that same chapter 4. Just go inside. You will see this S matrix. I don't know. I am not requesting you to study the things on equivalent voltages and all. That and all you don't do. That will all be too much electromagnetics. So I told you equivalent voltage is not required for you because the VNA does that job for you. The VNA gives out a matrix. You need to know how to analyze it. That is what we are worried about. And that is what all this S matrix thing is about. Right? So I'll stop here. Any doubts or any clarifications you would like to know? Because don't think that this S matrix class is over now. Tomorrow I'll be again starting from the same thing. And I have to give you some more insights into this. Right? So we'll stop. Anybody has any doubts or anything regarding this thing or any clarifications? Please go through the notes. Please go through the recordings correctly. And you can always ask me any doubts. If there are no doubts, the class is officially over. You can log out. Those who have doubts can please contact me. Ask me now. Yeah. Otherwise, those who wish to leave can leave. Thank you. Because it's already 9:45 and I think I have taken a bit of your time.
Thank you, sir.
Thank you. Anybody has got doubts? please feel free to ask.
Thank you, sir. Sir, can you tell me the name of the book of RF engineering?
Oh, I told you in the D.M. Posar, David M. Posar, Microwave Engineering. Akash, is it okay?
Yes, sir.
I think I gave it in the class clearly.
Sir, I was absent yesterday because of Viva, I think.
And that's okay. That's okay. Okay. Anyway, I don't mind telling that, but I'm just telling. I told you at least 2 weeks before. David M. Posar, Microwave Engineering. In that, go to chapter 4 directly. Chapters 1, 2, 3 are basic electromagnetics. Go to chapter 4, start reading it. That's what I'm taking in the class.
Yes, sir.